Okay, so anyway, this is a typical stoichiometry problem. And basically, what makes this problem different than all the others is we're starting with one chemical and ending with the other chemical. That is why we balance equations. Because we're not just staying with one chemical, we have up to now. The balanced equation allows us the ratio between those two, which is the middle step on stoichiometry problems. Okay, so step number one is balance the equation. So I'm going to balance it really quick here. So we're dealing with methane and water. And notice the coefficient ratio is 1 to 2. So for every 1 methane, we produce 2 waters. That's what the balance equation tells us, because the coefficients are 1 to 2. Okay, so we start with a given. Need to put water up here. Now I'm going to use instead of parentheses, I'm going to use a slightly different way to divvy this up. It's called train tracks. Now think of that vertical bar as parentheses. Okay, so step number one is our good old moles. Okay, so that's 1 mole over 18 grams. That's the molar mass for water. How did I get that? From the periodic table. Two hydrogens, 1 oxygen. Adds up to 18.02. Okay, so that's the first step. So we want to convert. Okay, the next step comes from the balanced equation. Okay, and we want the water to cancel. We're trying to calculate methane. I'm going to write the coefficients from the balanced equations there. Okay, water's 2, methane's 1. Okay, now we need to convert. Right now we have moles of water, or excuse me, moles of methane. So now we need to convert the moles of methane to grams of methane. So we need moles on the bottom, so it cancels. And let's see. So hydrogens are 1.01, carbon is 1201. So that's 1605 grams per mole. So what are we left with? Grams of methane. What are we trying to calculate? Grams of methane. So multiply everything on the top, divide by everything on the bottom. Okay, 3 sig figs, 4 sig figs. What's the 1 and 2? How many sig figs is that? It's not 1, it's not 3. Infinite because it's not measured. So that means these guys don't come into play regarding the sig figs. And there's 4 over here. So our answer is going to have 4 sig figs. So that's going to be 3 sig figs, sorry. So we've got, and then this last step converted. You convert the moles to grams of what you're trying to calculate. So for those of you who like patterns, this is a pattern. Everyone is going to be in 3 steps. Step 1 is you convert to moles. Step 2 is you do the mole ratio from the balanced equation. Step 3 is you convert to whatever you're trying to calculate. Yeah.
So you start with divide by
And then-
the two page 2.
Oh, I forgot about that. Yes, you should. You get 15.4. No, had I encountered this on the test, I would have marked off 1 for the answer being wrong and marked off 1 for the setup being off by a little bit. Thanks for keeping me honest. All right, so 3 steps. Now, there is lots of worksheets on Canvas files that let's you guys don't have to do this 2-step verification stuff.
Thank you.
Yeah.
For the problem, we still have to balance the, right? What carbon and what hydrogen is the problem with the top.
Balancing the equation.
We still have to balance.
Yeah, that's
the rules. That's how you got the 16.
That's why we balance. That attaches to chemical components. Yeah. How that. Okay, so files, unit 1. And at the bottom. Well, it's a good thing I checked. Anyway, there will be a number of practice sheets there. Yeah, glad I checked. Okay. So let's do some more examples.
President,
Yeah,
can you tell me how mole ratio is 1/2 again?
it's from the coefficients from the balanced equation.
Oh, the coefficient.
Yeah, so look at CH4, it's a 1, and the water is a 2.
So then, you exam something, are we gonna get that a balanced equation first then? Because we have to know that ratio.
You're gonna balance it. I'm gonna give you the equation, but you're gonna balance it.
Okay, so balance it and then.
That's why those 4 steps. Step number 1 is balance the equation.
The molar mass is how we got 16.05, right? This methane is 4 hydrogen, 1 carbon.
Yep. And the 1802 is from a couple days ago, the molar mass from periodic table.
So when we do these questions, you always have to convert to molar mass first, that's why it's.
Yep. Well, the first step is to convert to moles. So
Right.
if you're starting with grams, then you use molar mass. But what if you're starting with liters of gas? You don't use molar mass, you use the 22.4 liters per mole.
Because that's gas.
Or if you're starting with number of molecules. Let's say we had 7.6 times 10 to the 18 molecules of water. Convert to moles using Avogadro's number, 602 times 10 to the 23rd.
So these 3 numbers, we should memorize them or?
2 of them are constant.
Right.
And the other one you get from the periodic table. So the 2 that are constants, Avogadro's number, 602 times 10 to the 23rd.
Yep.
22.4 liters per mole, that's any gas. And Avogadro's number, it's any chemical. And then the third one is the molar mass from the periodic table, that's grams per mole. You add the decimal numbers up from the formula. Okay? All 3 of those can get you to moles. Or from moles on the back end, moles what you're trying to calculate as well. So you say you started with gaseous liters. I wanted to know how many grams of something else in the equation is. So then you can use molar mass on the back end. Front end, you're going to use the gas 22.4. So notice there's a molar theme in our stuff so far. And then it'll continue the rest of the semester. It won't continue into 306, however, because we don't do math in 306. Okay, so let's do another one here. Okay. Same reaction. Same balance. Okay, 34 grams of carbon dioxide are produced when methane is burned. How much water is produced? So, what's given? Carbon dioxide. Now, next week, we're going to learn about nomenclature and you'll know why it's called carbon dioxide. Okay. And what are we trying to calculate? Right, how much water is produced, so grams of water. So we go to up our equation, which is this. Okay, so blank coefficients means it's 1. Okay, so step number 1 is convert the grams to moles using the molar mass of carbon dioxide. So carbon, 1 carbon, 1201. Oxygen, 2 of them, that's 32. So that's 44.01 grams per mole. So step 1, convert to moles. Now we're at moles of carbon dioxide. So what's the ratio now? Carbon dioxide has to cancel. Water has to be on top. So water's 2. Carbon dioxide is 1. The carbon dioxide cancels. Now we're going to water. We want to get grams of water. We're going from mole to gram, so that's molar mass. So multiply everything on the top, everything on the bottom. Three sig figs, 4 sig figs, infinite sig figs, 4 sig figs. So 3 sig figs for an answer. So it's going to be notice that's a very distinct pattern. Very distinct. It looks exactly like this one, different numbers, but it's basically the same. Now, when I show you the practice worksheet, it's going to have answers on it. And you're going to look at the answers and you're going to see this exact same pattern all the way down. All the way down. So that's what's nice about the way we teach this, is we teach this pattern. And of course, the reason why the pattern is there.
What's the mole for gas? 20,
22.4 liters per mole.
but right here you put 44.
Because they're starting with grams. Grams of gas. You get moles of, you have to use the molar mass. If I started with liters, then you use the 22.4 liters per mole.
Liters of gas.
Let's do one with gas.
Grams of gas, 4.
Grams of gas, yeah, you use the molar mass for CO2, which is 4401.
Oh, I see. Grams of gas is on the periodic table.
Yeah, grams is, we use molar mass, no matter if it's gas, liquid, or solid. Because the conversion factor has to have that in it for you to convert.
Yep.
All right, so let's do this again using gas now. In fact, let's do gas the whole way. So Okay. All right, so you still need to do the balanced equation. Okay, so given is 34 liters of steam, gaseous water, also known as steam. Convert liters to moles. Now we need to go to the balanced equation. Now we're going to liters of methane. And we could mix up liters and grams as well. Yeah, when you're working with gases at standard temperature pressure, 1 mole of gas, any gas, it occupies 22.4 liters. Yeah,
That's how you got the 8.02 on the previous problem, that's grams per mole.
yeah, because we're talking about mass now of the gas. All gas has mass, even helium. The reason why helium floats things is its density is less than water, less than air. So it floats, not because it has no mass though. If this mass is less than nitrogen gas.
Does it matter where you place it in the problem?
Yeah. So the first part of the problem in converting to moles, take the given, convert to moles. The middle part of the problem is doing the mole ratio from the balanced equation. That's what we balance it. Then the last part is we convert the moles, what we're trying to calculate, to whatever we want, grams, liters, whatever. And again, 3 parts. Again, same thing. Stoichiometry is always in 3 parts. Yeah,
Carbon dioxide is produced when many, or how much water is produced. And you
Stop.
explain,
you mean this first problem here?
yeah, could you explain? Well,
Yeah. Carbon on the periodic table is 1201. Yeah, I just happen to have those memorized, but yeah. If you do this enough, and use the same chemical, you'll. Remember, I started doing this in 1964. I had kind of a head start on that.
Well, it's interesting. But I think sometimes you might convert it. Because it might be different, it's in things ones. Professor?
Yeah.
Can you show me how you chose the ratio? 1/2 or one CH4 to H2O? Yeah, but why didn't just pick this one? It's not very good. Why?
Yeah, like which one goes like fighting?
Yeah, the coefficients after you balance the equation is where I got it from.
Right, but I guess. Water is produced when methane is burned.
Right.
How many CH4 is consumed? So is CH4 my top number because that's the one I'm.
That's
looking
the one
for?
you're trying to calculate.
That's what I'm trying to calculate, so I
Yeah.
put CH.
The one on the bottom has to be what you're given. Because if it's not on the bottom, it won't cancel.
Got it. So, okay, I'm just have that, because we're trying to cancel it. And then what I'm trying to calculate is on top.
Every time.
Sure.
But it's good that it's every time. It's one less thing to know. Yeah.
So since gas was gas, the conversion is kind of. Like, you just put one. There's no
The
point in
22-4
converting it because,
The 24 cancels.
yeah, they cancel each other out, the conversion.
Well,
So you could
it's still
just-
gotta, it's still gotta be there. But the fact is you're using the inverse of the conversion and the output,
Yeah.
they cancel out.
Yeah,
Now, the thing with gases get complicated when you're doing stoichiometry, because if it's not at STP, then you have to use the ideal gas law to figure out what the volume is on the front end and the back end. So this gets still 3 steps, but the conversion is very awkward. Because this is the ideal gas. So N is moles. So this is what you use here. Or here, depending on if you're not working at
it's not
STP.
that
Yeah. So it puts a kind of a wrinkle in things, but it's still 3 major steps. Convert to moles. How do you do that with a gas? We need to know pressure, number, temperature in Kelvin, which is a temperature scale we haven't talked about yet. Okay, let's do one with particles. Any other questions? These are all good questions, you guys. By the way, most of my classes never ask a question. Hmm?
They never had.
Any questions?
Super, super.
Right.
You are. I mean, you guys ask a lot of questions, and I've done all these games to get people to ask questions. And none of it works. And every professor has got the same observation. How do we get them to ask questions? You guys have been great. Because if you're thinking of something, but don't ask the question, the person next to you could be thinking the same thing. For example, you were saying in that first calculation I did, I forgot about the 2 in the bottom. Did any of you else notice that?
Still trying.
Well, I mean, once you got things set up, you just multiply in the top, divide everything in the bottom. Yes, I understand. Okay, I'm gonna do one more problem using molecules. And we're gonna go, we're gonna start with molecule, and end with, say, grams. Okay, so, Okay, so this we're gonna mix up molecule, number of molecules and grams. Okay, so balance equation. Okay, so it's balanced. All right, we're starting with number of molecules, so 34.5. Now we're counting molecules. How many? That's Avogadro's number. We need water on the bottom, methane on the top. And then methane is it 44? No, 1605. Okay, step number 1, convert to moles. Step number 2, coefficient ratio from the balanced equation. Step number 3 is to convert to, in this case, grams. Again, 3 steps.
Professor,
Yeah,
I was just using that periodic table. And I got 1.0.
you know, if you round hydrogen to 101,
Is that what we're gonna do?
yeah,
Oh,
because the periodic table that I'm going to give you for the test has got everything is 2 decimal places.
okay, perfect.
Okay. Now. You're gonna have a take-home problem. Test one. At least one take-home problem, I should say. I'm gonna give you like 3 days to do it. Lots of time. One of them is gonna be a more sophisticated version of this. What happens when you are given two given instead of just one? You've never seen that before. You've always been given one given. What if you're given two? Okay, this went from a one problem to 5 problems. Okay. So let me show you what that means. Going back to the bicycle example. I've got 10 frames, 10 wheels. How many bikes? The given is 10 frames and 10 wheels. So how many bicycles can I make? Well, if I ignore the wheels, how many bicycles can I make? 10. If I ignore the frames, how many bicycles can I make? 5. Which limited the amount of bicycles? Frames or wheels? Wheels. So this is called the limiting reactor. And this is called the excess reactance. So what excess did I have from this problem?
So
5 frames.
5 frames. Five frames in excess. Because we don't have enough wheels to go around. And this is the essence of the chemical version I'm going to show you. And that's going to be your take-home test as well. Now, normally I do this in a regular year. I separate out what we've been doing for the limiting reactant one by days. And I tell you to go home and do this worksheet at home, which has got a whole bunch of practice on it. Unfortunately, because we're jammed into 8 weeks, you don't have a day separation. So, I tell you what, I'm gonna go over the problem and we take notes. And then on Monday, I'm gonna give you some more practice that, because you want to do it at home. In fact, yeah, I'm gonna do that. I'm gonna, when you guys start doing the dry line, is it, who in here has not done the dry line?
The worksheets,
Mhm.
is that what I gave out yesterday or?
The balance.
Yeah.
Okay. So everyone in here has done it, so we're not gonna have anyone in Thursday's dry line. Huh?
Those that you gave out yesterday?
yesterday.
Yeah, he did still, I wasn't, so, yeah. but-
And you- Okay. Guess what?
Yeah.
Okay, so let's do one of these. And just take notes. No, wait a minute. We're gonna do this on Monday. Okay, over the weekend, I want you to, I'm gonna post some, practice worksheet. In fact, I'm gonna post just one. But it's got quite a bit of practice on it. And I want you to do that for Monday. Because if you don't understand what we're doing today, you'll die on Monday. Because it's a lot of parts to it. Okay, so what I'm gonna do, I'm gonna cover some of the stuff on today, which is nomenclature, which is your next driver. With a new schedule. Okay, so what I want you to do is pull out from yesterday. The handout I gave you, with all the common ions.
Awesome. I'll be like, oh, did you see? Oh, see what you did? I told you, when you start dividing everything all in one bill, it's gonna have this shoot. I did this and I pressed enter. Yeah, because the path, you understand? I've never done it. Do you understand what I'm saying? When you start putting more and more and more together, it's gonna mess up because they don't know what to look, they try to multiply the times or something. I get scared when you start doing that. Not that you need to break down every one, right? But it's something is something. Then you divide that. But because the second you need, listen, because the second you need, because the second you need. Oh, you're crazy. Dividing. Dividing that. Crazy. Nothing else but
I need about.
Back there. Yeah.
Oh, I know what you did, look. I know what you did, look. I did it twice, so the first that I did. Divided by 6.83. Did you vote?
On this last one, with us, there, with the answer to that's the very beginning. Oh. Yeah.
Yes, yes. Yeah. I divide by this and then I divide it again, I infinitely divided. That's what happens. But then, let's get it.
All right.
I didn't work anything.
He told me I make the same mistake.
Okay. I'm gonna talk about nomenclature now. Okay, everyone. All right, if you look on the common ion chart I gave you, there are two kinds of ion. Now, an ion is charged.
That's a whole zip.
Now, what an ion is, the number of protons which are positively
I would say,
charged.
I would
is
say
not equal to
stickies.
The number of
It's
electrons.
gonna be way
which are
better than this.
negatively charged.
You-
That's so you've got a net
For a whole
positive
zip.
or a net
Yeah, you
negative
can't get-
charge on your molecule.
Yeah, you can't. I'll
Okay?
say that for
So if the
Yeah,
number
you ain't gotta
of
do all that.
protons is
Give us
greater
something to
than the
do.
number of electrons, what's the net charge? Positive. And that is called an,
What is it, 1250?
cation.
1250. Yeah. UV smooth, blaze it up. No, you good. It's gonna be bag ready for you.
And when it's flipped, where there are more electrons than
Damn,
protons,
bro, I can't do it, but I
and the
want to
charge
buy
is
one so
negative.
bad. I'll buy any
Okay.
one.
So there are
Hell
two
yeah.
nomenclature
Is this for
naming
a couple?
conventions. One's for ionic compounds, the other's for molecular compounds. Molecular compounds have
I'm mixing it
zero
with Indo.
charge, like
Dude, I'm
water, for
mixing it with
example,
the good shit anyway.
carbon dioxide,
I ain't tripping.
um, gasoline.
I'm gonna hold on this just because I can't buy weed for a while.
So those have zero charges. So those are molecules, not ions. And we're going to use the molecular naming convention for those. Okay, so we're going to do the molecular one
She was like, "What did I
today,
do?"
and I'll get into the ionic one on Monday. Okay, most people find the molecular one is easier than the ionic one.
Got some pain coming back.
Now, your common ion
Thank you.
chart,
Take care of.
you need to all come up and pat my back, because in
Hey,
the other
Gary.
305 classes, you have to memorize.
Your mic is on.
Thank God.
That's why you're getting those flashcards in your.
Oh my.
However, no one here does not own a smartphone. Gee, no hands are going up. Why memorize this thing and in 3 seconds on your smartphone you can find yourself? Sorry, but you're not, I'm not. Why memorize the entire periodic table?
Well, if they use, I think that's not memorized.
I took.
Well, I just find it fine. As soon as the class is over, you won't forget all this stuff.
You try to make it harder.
So why? And yes, I'm gonna have a test. Okay, on this, it's not totally ion. Look on the far right. It says covalent. What about covalent molecular? Those are two words that are learned. Okay, cations, positive charge, anions in the middle, negative charge, covalent, no charge. Now, we're gonna see on Monday with the ionic naming is built into the naming is net charge balancing. With covalent, there's no charge. There's no way to figure out the number of atoms of each. So there you have a numbering system built in. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona. Okay, all the way up to deca. Now in 306, you use the same numbers. And you use it every single day. So you don't have to memorize it, you use it all the time. literally, hard to stop. Even when you study biochemicals, a monosaccharide. That's one unit, glucose or fructose fluid. Disaccharide, 2 units. Trisaccharide, oligosaccharide is 10 or more, and polysaccharide is 100 or more. Those are the 4 basic carbon. Okay, all right, so let's talk about molecular or covalent naming now. All right, carbon dioxide. Why is it called carbon dioxide? Well, how many carbons are there? One is mono. So it's always going to be in 2 parts. Okay, so the first part of the name is from the periodic table. So what is C on the periodic table? Carbon. Okay, the second one is an ide. So look on your ion chart and find oxygen on there in the middle, towards the top. What ide is oxygen? The very, very top. Oxide. Okay, so we have 1 carbon. How many oxides are there? 2, so that's diol. So it's monocarbon dioxide. Now, like a lot of ones, it's optional on the first one. So monocarbon dioxide is a proper name, and so is carbon dioxide. Now, if the second one was a 1, you have to put the mono in there. It's not optional, only on the first one. So that's it. Say we were going to go from a name to a formula. Okay, pentaoxygen heptachloride. What's the formula? Look on the top right. How many is penta? 5. Chloride is hepta. How many is hepta? It's very straightforward. I'm going to find ionic is not straightforward. That's where we're going to wait. Now you can start on your dry lab on nomenclature if you want, and it'll also explain how to do it. Okay, let's do some more on this. Let's start from a formula. Okay, V3Br9. Okay, V is vanadium. Br is bromide. So we need to write. You see where vanadium is? Okay, so it's tri vanadium. Nona bromide.
I'm still confused, Preston. How are you getting are you getting tried because there's the V3? So yeah,
Three of them. So if you look on here, on the far right,
This chart?
Yeah.
Okay.
So it would be
Yeah,
no bromide.
Hmm?
There would be no bromide, and then the bromide of what's on.
okay, and Nona is 9. And BR is bromide.
No, that sounds like that's the octave sounds like any. Have this.
Yeah. The second one is always an I.
But hexagram,
The first one is whatever it says on the periodic table.
hex means 6 actually. Hexadecimal.
And then you need some
Heptadecimal.
modified concept.
Pentagon. Hexagon, hexagon, 6.
Let's do hydrogen peroxide, H2O2.
Peroxide.
Dihydrogen dioxide.
You saw the bottom, it says, organic acids. What was the?
Yeah, H is weird. Whenever it's associated with an acid, it's not a hydride. Minus H, it's a positive H. Okay, that's when we get to we haven't talked about acids and bases yet. So H is a weird guy. Some people put H in 2 places. They put it on the left and then the right next to helium. Because it acts like group 1 and group 7. Weird stuff. Especially when you take an electron away, you end up with just a proton, just a nucleus, 1 proton in it. If you add an electron, you've got, it becomes negative because it's got 2 electrons and 1 proton. And it's either way works. So hydrogen is, all the fancy math 150 years ago was done with hydrogen because it's so simple. Everything else, a fudge factor, we're doing this fancy math. But hydrogen is so simple. Anyway, that's why it's got a plus and minus.
Am I supposed to, are we supposed to memorize if you said hydrogen peroxide, we're supposed to know H2O2 somehow? Okay. You're gonna give us H2O2 and we're supposed to write dihydrogen dioxide.
Yeah.
That's what we're supposed to know.
I used to have a list of common chemicals around the house.
Yeah.
And next time we teach 3 or 4, maybe if everyone knows those. It's nice to know stuff around the house. You know, what's gasoline? What's ammonia?
Yeah,
Things like that. In
yeah.
fact, I'm gonna bring that back. I saw it in Washington a lot with the same class. Okay, well, that's it for molecular naming. Now, ionic naming will be charge balancing. It's gonna get more involved. Not horrendously more involved, but more involved than molecular or covalent. Okay, so that's it for today. I want you to do the worksheets I'm going to be posting in a minute under Files Unit 1 for Monday. I mean, if you don't do that worksheet, you're going to be hopelessly lost Monday.
Kind of quote, this goes
Yeah, stoichiometry practice.
That's the same. Like,